Good afternoon. My name is Pavel Tikhomirov. I'm from Virtuozzo company, and I do the kernel development and container part of our product. Many do containerization, but they seem to do the same thing. There's a lot in common. Today, I'll provide you a survey on what containers are made of usually. First, I'll provide the brief history of containers. Next, I'll tell about the parts of container skeleton, and I'll describe each of the parts in more detail. And finally, I'll tell you about the Unikernel. It's an alternative to containers. I'll tell you how it may be applied and what benefits it has. Now, brief history of containers. They appeared as a replacement for VMs, and virtual memory appeared in the middle of the last century. They worked well. It's a good, fast alternative. More containers may be placed at the same physical hardware than on the VMs with the same properties. But of course, everything costs something. What's the price? For containers, the main problem is security. It's explained by the fact that we virtualize the operation system OS kernel. Not like in the hardware virtuals, all the system challenges, all the interfaces of the OS must be virtualized and provided to the container. Hence, there are many more of those. And like in the supervisor, we control everything. All the requests go via us. And here we may be ignorant of something. Somebody may penetrate through our container and break everything. So we have a big area of attack, and we keep racing permanently. There's the kernel in which new objects are being issued, new features. And users, of course, want to use them right away within the containers, and all this needs to be virtualized, since not many think on how to make own features so that it works natively within the kernels. Thus, the biggest trend at present in containerization is application containers or microservices. With the help of application containers, we do the microservices. Within the container, just one application is started. It's easier to assess what it's going to do. We may trust it if we know for sure what it's doing. Hence, we avoid the security problems. Well, what are we planning to virtualize? We virtualize the kernel, as I have already mentioned, and that means we'll have certain standard objects to virtualize, like in the VMs. The processes will be started that will be started within the container need memory, disk, net work, plus some additional places so that the processes run on our Linux kernel. All the file systems, certain primitive interactions between the processes, the privileges for the processes, etc. That's what we are planning to virtualize. Next, how do we do that? What's necessary? First of all, we should limit the container resources, because the container is something that we want to give to the users on one physical node, many instances of the container. Hence, we need to limit the amount of resources used by the container so that one container doesn't eat up everything without leaving everything, everyone without it. Also, we should isolate the applications within the containers so that it works as if on a usual physical host machine. For that, we need the namespace technology. Also, before limiting the resources, we should provide those resources. We need to provide the main file system so that it may work with own files. Of course, we do not regard the spheric container in the vacuum. We should interact with it. And for that, we need to provide a network to the computer. When we have the microservice, certain web services get connected to each other, and in general, we get the SSM, the aggregated system. The first part of the container is the C group. For each resource, we have the controller, the CPU controller, the memory controller, block U controller, which limits the relevant resource. For each controller, we install the usual FSFS group. For each system, the hierarchy of this controller. That's the tree of directories, in which each directory is the C group of directories, or simply the C group. Each process for each hierarchy should be in one of the directories, and next, these directories set to the processes within them the limits, the hierarchy limits, or limitation if there are some C groups within, then the limits are on work for them as well. And if the process is in the C group, and then the next process, it will be born within it. We see on this diagram that the process may be in any C group and the hierarchy may be random. That's not the way to do it. It's a useless way. It may be done this way where certain applications eat up the memory, so they should be limited separately, and all the rest should be left in the route C groups. But for containers, this is not applicable, so we've done the C groups unified hierarchy. It's a simple one. There's one root directory. Each hierarchy has an absolutely similar tree. Within them, there's the directory of our containers. So the process in C group CT1, if it's the process from container 1, it's both in the green and yellow hierarchy, memory CPU. The C groups, of course, do have some problems. Not everything is smooth. Though containers have been developed for quite a long period of time, still certain problems do exist. For example, there's no soft limit for the kernel memory. For the usual one, it exists. For the kernel, no. Let me explain what it means. Let me mention that the kernel memory can't be reclaimed. It can't be returned to the system and swap it on a disk temporarily. So there's no soft limit. Soft limit is a kind of a flexible limitation. We say that the container should be within the certain memory interval from 0 to x. In principle, it may get more memory if it's available on the node. As soon as physically on the node memory is running out, then we'll get close to that soft limit. So we'll try to reclaim their memory, depending on how they exceed the limit. The more is reclaimed. That's we don't have such an option for the kernel memory, unfortunately. Also, it seems that memory C group protects us from creating many objects. In fact, no. We may, instead of doing the normal application, create one kernel object, a semaphore, one region of memory may be mapped into the file may be mapped into the memory. Instead of that, we can use aggressive memory. We take one resource, one kernel object, and with it we fill the whole kernel memory given to us. Then there'll be too many objects on the node, and searching will take longer. So the productivity of the node will get slower. So unfortunately, this is the situation. Yes, so for TCP buffers, there was a separate introduced limit to limit them with a smaller number than our limitation of the kernel memory, so that they don't eat up everything that the container is ready to provide. Next problem is well, how to set those limits. We have a container, for example, it was given some 10 megabytes. It started and right away it was killed. Nothing worked since it was short of memory. Well, we couldn't reclaim it. The killer came and killed it. We don't need such a situation at all. We want the applications to work. Hence, we need to solve this problem. Plus, the applications aren't always using the memory in a uniform manner. Sometimes they need 10 times more, but we have already limited it. Hence, problems are coming. So it's a difficult choice how to set those limits, how to choose them. Next problem is, since for each resource in Cgroups, we account how much of it we use at creation of a certain object that we limit resources of, and each time we have to shift the counters, and we have the nest of Cgroup, a lot of them are closed, so we have to move the counters onto each level. This also slows down the performance. It's a drawback, but you may live with it. Cgroups, yeah, we've invented them to limit the containers, but they should be also within the containers. I'll tell you about it on the next slides. They need to be virtualized as well. Last is a small example of the free utility. If you start simply in a mainstream container, you'll see that it shows the starts on the physical node. Not everything is virtualized completely. Of course, it's a view. It doesn't matter what we see. The main thing is that we're limited, but it's also bad. In the container, we should feel as if on a host. Namespaces. Namespaces, that's the next main piece that container consists of. It's called to isolate our ideas of the processor in the container about a certain. It should think that the resource belongs to it and to no one else. All the IT people, when come one after the other, when we locate, when certain objects, when PDs are forked upwards. So everything should work like on a node for each resources. For that, namespaces are invented. Every process is in one of each kind of namespaces. In one of the Cgroups in hierarchy, you'll see it on the next slide. Also, they are inherited on fork. If we've put it somewhere, it'll continue to give birth to its own children in this very namespace. It will not run away anywhere. So there's no CPU namespace, same as in free. So within the container, we may see how many CPUs there are on a node, how many are maybe started regarding the cleanliness, how many megahertz we have on a node, but in fact we don't have them. So for containers, it's unless your application knows that it's used in the container, so it's not relevant for it, then there's no problem. But the principle is not yet finished completely. We don't see everything like on a host. We view in a different way. Well, namespaces, same as the Cgroups, form hierarchy. Each, say, green, orange, blue, pid namespace, mount namespace, met namespace, they form hierarchy. So, in which namespace we create the new namespace, it becomes its parent. Well, also additionally to the Cgroups, to what we have in the Cgroup, though it's not mounted on the file system, but it's also a tree-like structure. Additional to that, we have the user namespace, the main, though it appeared the latest. We had to somehow divide subdivide the privileges for containers. We didn't want that within the container there's a user who wants to do a privileged operation under the root. We give them the root IUID, and then with UIDs and with all the capabilities, it can do something bad on the host. So we should have an allocated view on capabilities. He thinks he has all of them, and here, really, with their own resources, he has everything, but with host, no. So for that, we do UID mapping within the namespace, the user namespace. We see ourselves as user 0, and outside, there's some other random ID. Also, it should be mentioned that on the next slide, I'll be describing a small problem. Real IDs are stored on the disk. If we write a file within our container, it's not our UID 0 main root that is recorded, but 1, 2, 3, 4. Clear why, so that when different containers, when they get to the disk, it cannot get into somebody else's different disk when they get a view to it. If they view it, they can't enter it, since they won't have the capability for that. Well, that's the diagram with several containers. Container may shift from one node to the other. I won't tell you much about migration, but there is such an opportunity to move containers between the nodes just to balance the load. So what happens when the mapping of these containers is overlapping? We have container 1 under the host, which is mapped to 2039 UID. And the same container is on a different host that has come to us. Well, we have to survive it and to provide different user IDs to it. So we'll have problems on the disk. On the disk, all the old IDs of this container are recorded, so we'll have to rewrite them or to invent something cunning to shift them. So now we are working on the development of ShiftFS. This is yet a non-resolved complication with the namespaces. Well, the Cgroups. We've made them. We are now trying to catch our tail. We've made the object, and now we have to virtualize it again. So why do we need to virtualize it? As I've mentioned, the view is not completely virtualized. We see certain things on the host. To be able to view what is really in the container, if your application understands that it's in the container, it may need the Cgroup. So say they have files with statistics of resource usage. Also, it's possible that there's a case when, for example, you want to virtualize within your containers other containers. I know you like Docker. We start the Docker and Docker or Virtuozzo container. Hence, if you want to create containers within the containers and to somehow isolate and limit it, then you need to somehow provide the Cgroups. That's why the Cgroup namespace was invented. It's already a resolved issue. Yeah. If we didn't have the Cgroup namespace, let me explain what it is. If we simply provided Cgroups for a certain record, then the container may say, aha, I see the host Cgroup, I may record myself into it and get outside. Get, for example, all the memory or all the CPU. Get out of the limitation. So the container shouldn't be shown the host Cgroups of the other container so that it cannot transfer and account its activity instead of somebody else. That's why the Cgroup namespace was done. Only that subdirectory is allocated in which the container from Cgroup is working. It may only do things within it. Yep. In case of such an option, the container feels like on a host. Of importance is one more thing. the container should be provided files. The applications usually work with files. You cannot do without them. Thus, we need the file system. How do we provide it? We enter all these things, the user namespace, mount namespace. We copy into a certain file, which is allocated on the host for containers, all the files necessary for container, binaries, libraries, and other configuration files. The mounting devices, simple ones, and all this now is now up.
So we go to a special system call over there and start our application, which we want to start at the launch in the container. This is it. So our application already has the state in the container. Wait a little bit. At step 2, we had copying. Well, that's bad. So when we tested Docker our containers, everything worked at VFF above the regular file system. See, and the files copied every time when container was created, taking much of the space, which is bad. So that's why we have layers. It's a layered file system. DM thin overlay. So the difference is that sharing for files and blocks, the level is different. So we have the bottom, the base image. For all containers, it's universal. They are read-on only. You can't change anything. There is a special layer where to record new files and new changes. Very similar to copy on write. So if you write into an old file, so we don't create the new file, so everything is put into the new file, the updates. Then we have the container view, the third layer. It looks like all these files are merged, and we have the image, the old files, the updated and new files at the same time. So the advantages is to start container quickly, and file blocks are shared at the disk. You don't have to store a lot for containers. Plus MLA person, a node which we see inside the container. They are identical to the nodes in the base image. So when we upload into the memory, when we map it, when we access the file, we do just once for all containers using this base image. When you are attentive, that you would see that user win space will have some issues, because you have to shift user ID at the disk, because this image, base image, is to be used everywhere, which is kind of comprehensive, complex. Here we go. At the next bit, we talk about the network. So the container is not usable. You can't do anything within it. That's why we use the network namespace. So at the beginning, all network devices. So we just started the Linux. It's all put into one namespace with some exclusions. However, in a regular case, we create the network space for containers, and we have a virtual Ethernet device, which is in fact two network devices connected with a cord, and we send packages from one side, getting them at the other side, and they arrive to the other side. So it's easy, but it's done virtually in the core, and by sending packages from the internal device which is inside the container, we get it on the other side, and then we have routing, and then bring it to the network, similar to a regular router. MAC AIP VLAN is used when we share the same device by several users. So, and then they are sent into the network with MAC and IPs, and containers have their MACs and IPs through the physical interface using the VLAN, which is put inside MAC. So there can be many network configurations. And the very last thing related to containers, how to manage them. Because without container manager, you can't do anything. It collects everything. It collects and assembles namespaces, groups, other things, and identify the real position of the container. Because there is no such a thing as a container. In fact, several technologies are merged together. That's why we need the container manager to do it, as well as to monitor, to identify when it stopped, the container stopped, to have statistics. Also, there is a patch at mainstream, at LKML. It wants to have at the core a structure which would assemble things together. Then we'll have a possibility to invoke this command to start container, to stop container, and everything then will be done at the container, at the core. It's an alternative to the user manager. Let me brief you on Unikernel. It can be used against application container. If you have application container with just one application, the difference is in container. It's an analog to a virtual machine. So if you take a similar case with virtual machine, then you would understand up front there is a big overhead. Just for one process, you have, with several threads, you run the whole general purpose kernel. You will have to manage inter-kernel communication and the whole pile of processes. But we have just one process. It's a big overhead. So for microservice, you don't need to run the virtual machine. That's why there is an idea why we just don't get away with this interlayer, because we have just one process to manage, and it runs on top of the hypervisor. That's a unikernel concept. When you remove the core, the kernel, from the virtual, we become the kernel. libc library or any other library. It depends on the base that supports the application. So it gets the support of kernel functionality. Drivers for devices. Usually our operational systems have drivers for a number of devices. But if we run only on top of hypervisor, we know that it will be for virtual machines. Then we will need just one thing, the rest may be removed. Then a minimal support of the network to afford sending packages outside. You can use the entire memory, which has in this thin layer of our virtual hardware, because we are the only users inside this virtual machine. So physically, we can get addresses to the memory and or just shut down the virtual memory entirely. Then, because we are alone, there is no need for us to switch context from privileged to unprivileged. We are always in the privileged context. That's the habitual environment for the kernel. And due to all these improvements, direct address to the memory, eliminating certain switches, the overhead is much less. The layer is small, giving us the minimal support to launch the application. The advantages? of the approach. It works as fast as the container, more or less, and has the same security. Because everything which below the virtual hardware, we have the same as the virtual machine. This is the avenue for the future. What can we use for microservices instead of containers? Let me sum it up. My last slide, in fact, has a bit of advertising. We have this open container initiative to explore. This is a thing which standardizes all these things, like creating a container, managing it, storing disks and image disks and disk images for the container. You may go onto this website and see in detail how you may deal with it, like using Cgroups. Plus, these groups are available to everyone, and if there are two applications and you may run them at the same time, they may just be counterproductive and harm each other. I'm done. Thank you. Thank you for your time. Questions? Thank you to the speaker. And we have the first question. Thank you for your presentation. Can you give more details about advantages of having containers in the kernel, in the object's kernel? When we operate from the user space, our access indirect, we just can't have we cannot put just the direction sign to namespace. So we can big mount references from processes to then have some access to the namespace and know its whereabouts. Like very often the network namespace operate when all processes are already out, and you may lose things. It is too complicated, but by creating a container, we have all links in one space. My second question, are there any options how to implement Unikernel? The answer, in fact, there are many projects already available. I cannot give you them at the top of my head at the moment. Thank you for your presentation. I have an interesting question. I faced a situation with containers, and you had it in your presentation. You talked about free utility, that it doesn't work correctly at containers. My issue is sometimes we use external applications written by somebody else, and we face issues. If it's already packaged in a container with host virtualization, so we don't have the quantitative data on memory. Would it be possible in your case, if there are issues with the application? Yes, there are counters on the memory group giving you information how much is used by the Cgroup at the moment. They are kind of clever, and it gives you the memory logged by a certain Cgroup. There are many applications which already know that they will they would be launched through containers, and their start is from Cgroup. Thank you. Cadvisor would be my recommendation. One more question. Thank you for your presentation. When it comes to Unikernel, UFC, which starts from container, it cooperates indirectly with host through hypercall and it cooperates with hypervisor. So it's starting the entire virtual machine. There is no direct cooperation with the kernel, interaction with the kernel. CFC usually does inter-system calls, and the answer, there is a minimal support in Unikernel. All main system calls needed for your application to support it. Unikernel, it's like so you cannot start any application with it, but we know what it does, and the support is afforded through libc. Am I understand correctly? Do I understand correctly that they are custom dependent? Well, it depends on the application, but indeed applications are kind of semi-customized. So with Unikernel, what is the function of the virtual equipment? Similar to the virtual machine. It's virtual equipment offered to the inside the virtual machine, virtual memory, virtual disk, and libc calls them as internal objects. So this virtual equipment is also specific? No, it is not. It is identical to a regular virtual machine equipment. Well, in the virtual machine, this equipment is controlled by drivers. I understand you. So we put into the libc the minimal support needed for operating the application. Good afternoon. Thank you for your presentation. I have a couple of quick questions. I think we mix containers and virtualizations as it's a confusion of terminology. Container is isolating a process. Cgroups are optional. It very much depends on your definition on the container. Containers do not exist in reality. So everything, all technologies that we can use, so you can't call them containers, but this is a set of technologies giving a service to the customer who thinks he is at the host. Can you call Python as Python? Can you call them containers? Virtual machine can be container. Any application can be a container in this case. Containers, as we understand them now in Linux, they are namespaces and Cgroups, and they do not mean emulation the central processing system. And there are some specifics with working with schedule. It's not virtualization per se. And container namespace doesn't mean that it would virtualize for you the central control unit. And now inside a container you would see a couple of central processes. There is no magic. Indeed, there is no magic in what we do. I'm just giving you an idealized concept. We launch a program, it uses resources, and we give to this program some limits, so it cannot impact any other program. And as if it were a real physical node with X memory, and it's done through Cgroups. Then we take namespaces, and if we could have told this program you have just one CPU, and then it would have been to the virtualization through the virtual machine, because we just give one or two, depending on the money paid. You're talking about virtualization through hypervisor. My second question, security and containers through namespaces. And you said that we do not move our CPU into the protected mode, and we use the real module, and we face the security challenge. So the Unikernel is like a virtual machine. What's the issue here? We can break only at the hypervisor level. So if something goes wrong, then the whole system is corrupted, and the host either dies or we get access to everything. But if you break something at the superstructure, then it's a different story. Unfortunately, the asker is not using the microphone. There is a discussion now. We are coming to the break, and then you will have a discussion during the break. Let us thank the speaker and go for the break.